Welcome to our webcast, Core Process Pull, Little's Law in Action. This is the second of 3 sessions in our Summer Master Black Belt webcast series. I'm Larry Goldman, Vice President of Marketing for MoreSteam and the moderator of the webcast. We anticipate an hour for this event, which we're recording, available via the MoreSteam.com website, along with the slides and a Core Process Pull sizing worksheet. Here's a brief agenda for today. We'll begin with a short introduction, followed by the Core Process Pull lesson. We're planning to leave about 15 minutes at the end of the webcast for Q&A. All attendees will be on mute for the duration of the webcast. If you have a question you want to ask, please use the GoToWebinar Questions dialog box on the right side of your screen. If it's collapsed into a small toolbar, just click on the top expansion arrow, write your question in the box, and press Enter. We'll try to answer as many questions as we can in the time we have. A little about MoreSteam.com. For the last 10 years, we've been the leading provider of online Lean Six Sigma training and technology. For individuals, we offer all levels of belt training, Design for Six Sigma and Lean courses, short courses, engine room and data analysis tool, and green and black belt certification. Our courses emphasize interactivity, depth of knowledge, flexibility, and affordability. For our enterprise customers, we deliver customizable courses, project tracking and online testing tools, and classroom simulations for Lean and DMAIC projects. In the spring of 2010, MoreSteam and the Fisher College of Business at The Ohio State University began to jointly offer an innovative Master Black Belt development and certification program. The program includes 4 weeks of training, 2 of them online through the MoreSteam portal, and 2 of them on the live at the OSU campus in Columbus, Ohio. These can be started at any time and taken in any order. Again, the focus is on convenience, content, and affordability. The training program covers the Master Black Belt body of knowledge and topics ranging from advanced DOE to advanced Lean tools to leading change to financial analysis. The faculty includes professors from OSU and trainers from MoreSteam and Minitab. The certification process follows the successful completion of the training. For more information, you can visit www.moresteam.com and the link that we have here that you can see on the slide. It's now my pleasure to introduce our presenter for today, Dr. Lars Maaseidvaag. He's the Senior Master Black Belt at MoreSteam.
Thank you, Larry.
Oh, Lars has worked in the Lean Six Sigma. I want to say nice things about you, Lars, here. Hold on. Lars has worked in the Lean Six Sigma and process improvement industry for over 20 years, with 11 spent at the George Group, now Accenture, as a trainer, coach, and curriculum developer. His experience spans all industries, and his current interests include blended learning, process simulation, and mathematical optimization programming, which he earned his PhD. The Master Black Belt topic for today, Core Process Pull, Little's Law in Action, is just one of the topics that Lars either teaches in the live advanced Lean training or has developed for the online Black Belt module. And with that said, over to you, Lars.
All right. Thanks, Larry. Sorry for jumping in there a little quick. I wanted to get going here. So, like Larry said, today we're going to talk about one of the first topics that we have in our Master Black Belt series at MoreSteam, and we call it Core Process Pull. And really, Core Process Pull goes back years and years and years, all the way to the original development of Little's Law, when the initial relationship between lead time and work in process was discovered and identified and whatnot. So, Core Process Pull. And pull systems in general in the Lean world. We might ask the question of why would we bother with pull systems and whatnot versus a push type of system. And really the reason that we work with pull systems in a Lean environment is pull is the ultimate voice of the customer. It is the customer finally saying they want one of our services or our products. And so it's the ultimate expression of that voice of customer. Now we can satisfy that voice of customer and that demand either by replenishing a buffer in a make-to-stock type of environment, and our customer simply pulls from that buffer, and then that buffer through a replenishment pull system would replenish itself and fill itself back up again as needed. Or, alternatively, we can actually trigger a core process to begin and go through the steps of that process in a make-to-order type of environment. So 2 different types of pull systems, a traditional replenishment pull, where we're making to stock, or a core process pull where we're making to order. And these core process pull systems have gone by many names over the years, and we've settled on core process pull as it helps identify that this is truly our core process, whether it be a final assembly operation or manufacturing operation or a service operation where we are responding directly to customer demands. We identify it as a core process as opposed to a support process or replenishment process. And some of the other names, back in the George group, this would have been called generic pull system for those that might have been trained through the George group materials. And back in factory physics, by Spearman and Hopp, it was referred to as a CONWIP system, constant work in process. So it's been around for years and years in lots of different guises, but effectively it gets right down to the practical application of Little's Law. If we look at the differences between a core process pull, replenishment pull system, first and foremost, a core process pull is focused on a process. So the pull system control mechanisms are looking explicitly at a process, as opposed to a replenishment pull system where sizing in the pull system is focused on a particular part and maintaining the stock levels of that part in a particular buffer. So two different focuses here, a focus on a process versus a focus on a part. In a core process pull, we are actually controlling the work in process to specifically set and determine a lead time for that process, as opposed to a replenishment pull system where the lead time of the replenishing process is one of the many inputs that goes into the sizing of that replenishment pull buffer. So that's another difference. Like I said on the first slide there, core process pull is a make-to-order environment where we're not going to signal the process to begin working until we get an actual customer demand, versus a replenishment pull where we, based on historical information, size our replenishment pull buffers and then make that to stock. We still don't trigger customer demand of that and the replenishment of that buffer until we get customer, but we do pre-populate that buffer, that replenishment pull buffer, with some stock in anticipation of customer demand. Another difference, core process pull is truly applicable absolutely everywhere. And whether it be a shop floor manufacturing environment or a transactional or service environment, core process pull and containing and capturing the amount of work in process that we're going to allow into a process is really applicable absolutely everywhere. Replenishment pull on a large scale is typically more of a manufacturing type of environment. There are certainly applications for replenishment pull in, of course, warehousing and stocking, and even in the service environments, supplies and whatnot can be managed on a replenishment pull or a easier to implement variation of it, a two-bin replenishment pull. But the large scales implementations are more in a manufacturing environment. Now, as far as how we can actually implement these two different pull systems in terms of the actual control mechanisms, that's actually the same between the two. We can have physical kanban cards, we can have electric signals, we can have bins, we can have any type of storage boxes or whatever moving in either one of these types of pull systems. So they're very common in that sense. So let's deep dive a little bit into the design of a core process pull system. Bringing Little's Law back to the picture, and hopefully we're all quite familiar with Little's Law. Total lead time through a process is equal to the work in process divided by the throughput or the exits or exit rate of that process. And so that's a pretty basic relationship that we should hopefully all be fairly familiar with. Now, total lead time, in the sense, encompasses all aspects of that process, both value-added time and waste time. So we have the true on-tool or value-added time that's being performed on the work that's moving through that process. But we also have all the queuing time, the transportation time, rework time, all of that comes together in total lead time. Now, the question can become, is total lead time something that is explicitly set by your company or organization? Is it something that the customer sets for you and they have a particular demand that must be met? Or, like many organizations, is it something that just sort of happens? And over time, we develop into habits of lead time through a process is, say, 3 weeks, and kind of is what it is, and sometimes it's 2 weeks, and sometimes it's 5 weeks, but it's not something that's explicitly controlled, but rather something that just is experienced by the organization. So in a lean transformation and in the Lean Six Sigma world, we want to certainly make that something that's not just observed and experienced, but something that's designed so that we have a specific lead time that we are going to target and hit, and we have the tools to make that happen. If we look at throughput, throughput is determined by the capacity of our bottleneck step in the process, and all of the components of overall equipment effectiveness go into to what might be our throughput. If we look at the work in process, WIP is rarely managed directly. Over and over again, going into different client facilities, I'll hear the phrase that we can't finish something if we don't start it. And so WIP is pushed into a system and started without any regard as to what that impact is going to have on all the other parts or items that are already in process and what impact that on the lead time of the process. So in a core process pull system, we are going to be explicitly managing that work in process and sizing that work in process in relationship to our capacity and our demand so that we can hit a specific target total lead time. So in the end, we are going to be controlling WIP, and we can control WIP in several different ways with different mechanisms, but in the end we have to control that WIP and make sure that we then get a stable lead time through the process. All right, so if we look at the work in process versus lead time relationship as expressed by Little's law, as WIP goes up, lead time goes up, and we get a straight line relationship like we see with the red line there. So that's a pretty straightforward scenario. Now we do have a special condition that we have to take into account. If we were to calculate total lead time for a process and take the WIP all the way down to, say, one piece, even if one piece was really not enough work in process for our process and we were starving our bottleneck, but if we took that WIP all the way down to, say, one piece of WIP, we still wouldn't have nearly zero lead time. We would run into a minimum, and that minimum is the value-added time that it takes to actually produce that item or produce that service. So if it takes us 20 minutes to produce our service, and Little's law might say that with only one piece of WIP in the process, it should only take us 2 minutes. Well, we have that lower boundary of the value-added time. So the effective curve that we're dealing with here looks more like this, where we get down to that value-added time lower boundary, and we will never lower our lead time below that pure value-added time. So that inflection point in that curve, we're going to call this starvation boundary, or this lower limit of Little's law, that below that point, lowering WIP below that point, Little's law becomes invalid because we run into this boundary of the value-added time. Now where to calculate, or how to calculate that starvation boundary where we're going to begin starving our bottleneck, we can use this simple equation here, and we look at just the lower boundary of Little's law is going to be the sum of all of the task time of all the steps of the process. So if we're thinking about a process that might have, say, 4 steps in it, and we've got some transportation time and some queue time and whatnot, we've got all the time that's involved in getting through those 4 steps, whether it be value-added or non-value-added. We're going to sum up all of that time, and that's going to become our numerator. And then we take just the sum, or the total task time of the bottleneck, and divide that into the sum of our task times, and that will give us our lower boundary on the amount of work in process that we might have. Let me show you a couple different examples that might help make a little bit more sense. Say we have a process, 4 steps, and each step in the process takes 10 minutes. So the total amount of time that we have involved here is 40 minutes to get through those 4 tasks. And our bottleneck is any one of those, since it's a perfectly balanced process, so divided by 10, 4 pieces of WIP. 40 divided by 10. And that makes perfect sense. 4 steps, each one equally balanced. Therefore, we need 4 pieces of WIP so that everybody's working on something at once. Let's take a look at another scenario. Say we have a situation where we have 1 second in the first step and 1 second in the second step and 7 seconds worth of work in the third step, and then 1 second or 1 minute worth of work in the last step here. I think we were talking minutes above. So we still have the same sum of 40 across all of those, but now our bottleneck is actually 37, which if we do that division comes out to 1 point plus a little bit, 1.03 or 06 or so. So in this case, we're actually saying that we really don't need 4 pieces of WIP. We need just a little bit over 1 piece of WIP in the process. Well, that makes a lot of sense actually when you look at what's going on in here. If we had our 1 piece of WIP here at our bottleneck and they were just beginning work, we'd have the first minute of work, the second minute of work, the third minute of work, on up until we got to the 35th minute of work. And only at that 35th minute of work, when we're going to the 36th minute of work in our third station, that's when we need this minute of work here on our first station. Then we go to the 37th minute of work, and then this piece can move from here to the second station and do its 1 minute there. And then the third station finishes its work. That goes to the fourth station, and then this piece begins its work there. So in a very unbalanced process, we actually need less WIP. When our bottleneck is a very dominant bottleneck in terms of task time, we need less WIP than we would in a balanced process. And so this calculation down here at the bottom of the screen gives us that lower limit on where our WIP can be, that starvation boundary. Now what about WIP versus throughput through the process? So if we look at this relationship, we have our starvation boundary here that we've carried over from the previous page. When we get to the point where we are right about to starve our bottleneck, but not yet starving it, we will be at the maximum capacity of the process, right? Our bottleneck will be working continuously. We won't be starving it. Anything below, any amount of WIP below that starvation boundary, and we'll actually starve the process. And so we will see this point here where we are operating our bottleneck at full efficiency and there's no lost time. Any WIP level below that will yield a decrease in the throughput or the output of our process because we're beginning to starve that bottleneck. And so we see that type of a curve. And as our WIP goes down to 0, our throughput will go down to 0 as well. No WIP in the process, therefore no output in the process. Now, adding WIP above this point does not improve our throughput at all. We're up at capacity, our bottleneck is working, and so we remain flat from there on out. So any of that additional work in process that we put into the system doesn't buy us anything in terms of output. It only delays our total lead time by adding queuing time to our process. Now, a little bit of a nuance here. As we get more and more WIP, and we get way out here to the end where we've got lots of work in process, and this could be parts on a manufacturing floor, this could be emails in an inbox, or this could be loan applications or mortgage applications that we're trying to process. As we get more and more and more WIP, we tend to start having issues of having to switch between those different tasks, trying to keep up on everything, and doing a lot of switching, or on the shop floor, searching around trying to find the next part to work on. And so what we actually see is as WIP becomes excessive, we actually start to see a degradation in our throughput because we start wasting our operators' times looking for whatever they're supposed to work on next. We actually have another boundary here. We have the starvation boundary on the left, and then we have an excess boundary on the right, where if we cross that excess boundary, then we actually start to experience this destruction of our capacity and our throughput capability. So clearly we need to find the right level of WIP somewhere in this area here where we're not starving our bottleneck, but we're not putting excess WIP into our system so much so that we begin to cause that damage. So jumping over to implementation here, if we look at implementation sizing, We're back to looking at our curve here of lead time versus work in process. And clearly over here below the starvation boundary we have too little work in process because we're actually damaging our throughput at that point. And above the excess boundary we have too much, again beginning to damage our throughput. And we also have the negative implication up here of a very high total lead time because of all that extra WIP that we have in the process. So then the question becomes, where do we need to be in this central area here? Perhaps down towards the low side, perhaps up towards the high side, and a number of different factors are going to impact where we actually operate in that section of our line. Excuse me. And one of those factors is the amount of variation that our process experiences. If we're working in a world with relatively little variation, and that's variation both in terms of our customer demand as well as our service time in providing whatever product or service that we are. So if we live in a world with relatively little variation, then we can afford to operate down in this range closer to our starvation boundary. We can operate closer there because we don't have variation, and so we have relatively little chance that various randomness would cause us to move below that starvation boundary and starve our bottleneck and therefore lose capacity. So with relatively little variation we can operate safely down in this area here. With more variation we're going to be operating with a little bit of extra WIP in the process in order to buffer against that variation that we have not already taken out of the process. You know, if we're up in this area with more variation and perhaps high variation, then one of the things that would tell us to do is take a look using Lean Six Sigma tools on how we can reduce some of that variation and move ourselves down this curve and get the benefits of less work in process and therefore a shorter, faster lead time through our process. Now, how we actually find out where we need to be area, we can calculate the starvation boundary, we can look at where we are, and then we can really arrive at the optimum level of WIP really through either working our way down to the different levels of WIP as we bleed WIP out of the system and waiting for the system to stabilize. So we're going to work our way down. We're probably going to decide on where we want our WIP based on some particular target for lead time. So it's probably going to be a customer policy type of decision that's going to tell us what lead time do we want to achieve, and then we can draw that across and understand what WIP level we need to be at. In fairly complex processes where we're having lots of different steps going on and perhaps a process that has a lot of variation in mix, it might be difficult to always identify where our bottleneck is or our bottleneck will be moving quite a bit, and that's where we might go into do some process modeling and some simulation modeling to try to understand the amount of WIP that we need to have in our process in order to keep our very hard to find moving bottleneck running stably and consistently. So that's implementation sizing, a little bit on implementation sizing. Implementation scope. So where do we actually put these core process pull systems? Remember, core process pull is nothing but containing the amount of WIP in a portion or in a process, or portion of a process or a process. So the system boundaries for a core process pull must, of course, cover the bottleneck process, and then they must cover everything upstream of that bottleneck process, because everything upstream can work faster than the bottleneck. Therefore, we don't want any WIP accumulating upstream just because we, say, blocked it from here. We want to make sure that we include from all the way upstream in our core process pull. Any steps that are downstream of the bottleneck will be running faster than the bottleneck by definition, and therefore they don't need to be included in the core process pull boundaries because they're running faster. So the first thing we can see in this process that I have on the screen is we have some replenishment pull buffers stationed in this process that we have here, and these replenishment pull buffers decouple this top portion of the process and this bottom portion of the process, decouple those from the main process here. So that allows us to manage each of those pieces of the process separately. And then we see our bottlenecks, and then we see our upstream stations for those above those bottlenecks. In blue now are all of the stations that we need to control in our core process pull. And we'll actually set up in this scenario 3 different core process pull systems. Core process number 1 will manage this top process. Core process pull number 2 will manage this main process that actually makes to order for the customer. And we could certainly extend this scope all the way to the end station here if we wanted to, and include steps, this last 2 steps here, 6 and 7 in gray. We could include those 2 steps. They typically won't have a lot of WIP in them because they're running faster than the bottleneck. So at times it may be most convenient to count the amount of WIP going in at the beginning here and count the amount of WIP going out at the end. That may be the most convenient way for managing the system. If so, we would include all those steps. Minimally, though, we do have to include this span from the bottleneck forward. Down in this last process, core process pull number 3, our bottleneck is actually the first step in the process, so that's really the only one that we need to gate and control the amount of work in process. Now the mechanism that we might use different mechanisms. We might actually have, say, bins that are moving here in this first process, and those bins, an empty bin would be a signal to start a new batch or something through that process. We could have electronic signals down in this process perhaps, and we might have kanban cards or something like that down in this process. So we can have different mechanisms intermingling in the same organization on the same shop floor. We just choose the most appropriate mechanism for managing the process in the environment that we're in. Implementation timing. So what we always try to do in the lean world is approach things in a cautious and incremental continuous improvement type of mentality as opposed to a dramatic quick change. So most organizations, when we start looking at implementing a pull system, we might find that they're all the way up here on the top end with quite a bit of excess WIP in their process, and they need to figure out how to get, say, somewhere down into the into the center spot of this this good amount of WIP between the starvation and the excess boundaries. Now, what we don't want to do is just pull out a ton of WIP, and expect that we will safely arrive at that new lead time situation. When we pull out that much work in process, the biggest risk we have is that we haven't necessarily completely understood our process. Perhaps we've misinterpreted some of the WIP that's in the process or whatnot, and we might get it wrong, and we might overshoot our target and end up starving our bottleneck. And I've had many, many client situations where that's happened. What we advocate instead is a stair-step approach where you work your way down and let the process stabilize at each of these new levels so that you can make sure that your understanding of the process is correct and that the process will stabilize and still operate at each of these steps. And so we work our way down in a stable, continuous improvement scenario as opposed to one quick draining of all the WIP and hoping that we got it right. As we're draining down this work in process, one of the things that we'll often see with Little's laws, if we go ahead and count up all the work in process that we have in a system, and we look at the throughput that we had out of that system, we might get a Little's law result that seems to be higher than what we're actually observing in terms of units that are coming out of the process. So if we're observing total lead times through the process of, say, 5 days, but Little's law says it should be something more like 8 days, but we're observing 5, that is a sign to us that we probably have some inventory, we probably have some WIP that is not moving. So for some reason, something is not moving in the process. It may be that it's some dead inventory that is still on the books and still stuck somewhere in the process, but isn't ever going to be used. And so we counted it when we did our Little's law calculation, but it's actually not moving, and therefore it's not in the way of the other WIP that's truly moving through the process, and so we get an observed process lead time that's shorter than the target total lead time that Little's law said we should have had. So you do need to look out for WIP that doesn't move in the process. Some sort of obsolescence, spare parts that are going to be very slow moving, something like that, that's the process. And then you come up with some timing to work your way down, and how long it takes you to work your way down and how many steps you need to take, that really varies from implementation to implementation. I would say at the very minimum, you would never have fewer than 5 steps in your transition down. And so from the WIP level that you have to begin with to the WIP level you want to get to, calculate that gap. At the minimum, break that gap into 5 equal steps and work your way down through those 5 steps, making sure to stabilize at each of those different steps. If you're talking about very large levels of WIP, where you're perhaps going to take your WIP from 100% down into the range of 10 or 20%, then you're probably talking more like 10 steps to get from where you are to where you need to go. All right. So a little bit of a summary about what we've talked about today, and then I have a simulation that I'll show you. Core process pull. It's a simple system to gain control over a process, stabilizing this total lead time. Now, core process pull is something that you can really implement virtually immediately in any process, whether it be manufacturing or transactional. Implement it right away, and by doing that implementation, we start to stabilize our process immediately. At MoreSteam, we talk about the idea of containment. So a core process pull system is something that can quickly contain the damage that we're doing to our customers by stabilizing the lead time. It may be a grossly inefficient process that takes far too many resources and has far too much rework and all the other 7 forms of waste. So it may be a very inefficient process, but by at least containing that moving total time and containing that variation, we begin to stabilize the process and at least not transmit that inefficiency to our customers. So it's a simple system to gain control. It's very well suited to transactional and manufacturing environments. It's a great tool in transactional worlds where we really haven't thought of things in terms of work and process. And therefore, work and process has been allowed to fluctuate wildly with big highs and big lows. All right. Like I said, it can be considered and implemented very early in any continuous improvement project to help stabilize. Really, I mean, as soon as you've done a 5S to get the rubbish out of the process, then stabilize the process with a core process pull. And it's a key foundational component of any lean transformation. Now, let me hop out of the presentation here for just a moment. And show you the simulation that we have. This simulation is built in a product called Extend that we use at MoreSteam, as well as, and it's a discrete event simulation engine. And this type of process simulation modeling, as well as process optimization modeling, is a central component of the Master Black Belt program at Ohio State University and MoreSteam. We're really learning the nuances and the depth of the lean tools by building simulations of them. So we learn both how to model our processes, as well as some of the nuances and intricacies of the lean tools by using these types of simulations. So in this simulation, and I'll start it going here, in this simulation here, we see a number of different things happening. We have, on the top of this simulation, we have a push system where we're, by forecast, pushing work into this process, this 3-step process. And on the bottom, we have a core process pull, a pull system. Now, both processes are receiving the same customer demand inputs. So you'll see customers that just appeared here, and they pulled their finished goods out of these 2 buffers. Here's a finished good item here. Here's a finished good item with a Kanban card attached to it below. and the customers are pulling those away. And you'll see that the customer demand comes identically to both processes here. It's randomly generated, but it comes identically to both processes. The forecast varies between 3, 4, and 5 units that are going to be showing up and pushed into the process, and that is exactly at the average consumption capacity demand rate for the process. So they really are very identical processes in terms of their demand and the randomness of that demand and the randomness of the service times. In the above process, we're pushing work in. Our bottleneck, which is our middle station here, will end up being backlogged, and work will continue to push onto that person even though they're backlogged, versus our core process pull system here, which is just sized for 3 pieces of WIP with our 3 kanban cards. And you'll see in the bottom process here that we're not getting excess WIP pushed into the system because we don't get to start new work until this kanban card here on the right gets pulled off of that inventory and flies back over to the left and authorizes the beginning of work at our first station. If you look at our results over on the right here, we'll see that sales is equal to 10 for both of them. Right now, average wait for the customer is still 0. We haven't had any delays in meeting customer needs. The inventory for the push system is at 5.2 versus 2.4 for the pull system. And our total cycle time or total lead time through the process, because of that excess WIP, is at 3.9 for the push system and at 2.5 for the pull system. Now we're just at sales of 13 here. I'm going to turn the animation on and off, or off and on, just for a moment so we can kind of jump further down in time in this process. So flip it off and flip it back on again. Now you can see we're up to 751 in sales. So it runs very quickly without the animation on. What we have now is we've got a whole line of customers that are queued up behind our push system here, waiting for inventory, waiting for finished goods. We don't have anybody queued up on our pull system. Our average inventory of our pull system is still at 2.5 because, again, it can never go above 3 because we only have 3 kanban cards. Average inventory in our push system is higher, yet still we have an average weight of 10 here, average weight of 0.009. Now, this process is actually sized at about 95% utilization. So that's a fairly high utilization rate. And in a high utilization system like that, any lack of work at the bottleneck is going to cause a process to lose that capacity and have a tough time ever catching up with that again. And in a push system, we have no mechanism for really managing that WIP and keeping it in the right place. As processes get lower and lower utilization, so if we're down in the 50 or 60% utilization range, the impact is less severe. But certainly in transactional world, we're tending to look at processes that are designed to be very highly utilized. And in the manufacturing world, we're shooting for higher and higher productivity as well, and therefore higher and higher utilization. And it becomes more and more difficult to very carefully manage the WIP and how that WIP moves and when work is authorized. Ideally, we will have a system where the lead time that it takes to get through our process steps, however many process steps that may be, that lead time, our normal lead time for any product or service to get through those steps of our process is so short that it's short enough to meet customer expectations of that total lead time, even if those expectations change. When we get to that level of performance, our customer expectations and our customer demand, our voice of customer can change as often as it wants, and we simply introduce that change as the next item going through our process, rather than in this top scenario here, where we have excess WIP already in the process that we would have to work our way through and excess lead time before we'd actually be able to get those new customer demands and that new voice of customer reflected in the output of our process. So we use simulation like this, and we learn about process simulation, both discrete event simulations like this, as well as mathematical optimizations, and that becomes that's a key component of the Master Black Belt course at Ohio State and MoreSteam. So let me stop this and hop back over to our PowerPoint presentation. And then I think, Larry, we're probably ready to go ahead and open it back up for questions.
All right. Thanks, Lars. That was great, I think, especially the simulation. Well, this ends the prepared portion of the webcast. And as I said in the beginning, we've got about 15 minutes left over for Q&A. If you have questions you'd like to ask now, the question screen that GoToWebinar provides, and those will appear to me, and I can read them off to Lars, and we can address them. Actually, a couple things have come up already that I think are a great way to start. The first was people that had maybe wanted a few more examples versus some of the theory that you talked about. Perhaps you mentioned transactional was a great way to apply core process pull. So maybe from your experience, maybe some stories or a couple examples you can think of that might flesh this out a little bit.
Absolutely, yeah. I'd say the most common example of a good core process pull in a non-manufacturing, non-physical item environment is actually in engineering. And engineering in a manufacturing company, if we looked at the engineering change process, this is all transactional work. It's all service work of engineers making design changes and whatnot. And typically, in a process like that, we will have items that come into a queue up front and then are parsed off to a number of different engineers. And then those engineers work on those items and eventually get them done, right? And the engineering change orders are completed and implemented. Now, each one of these engineers in this scenario basically just keeps getting engineering change orders added to their table. Whenever anything comes through, it just flows right through that initial buffer and is immediately assigned. And so engineers might be sitting with, anywhere from 10, 15, 20. I've seen examples where they have 50 different engineering change order requests at any given time. Now, with having all those pieces of work on their desk and having no control over that work in process, well, Little's Law alone says that if we have, say, 50 pieces of WIP there in the form of engineering change orders, and we have, say they're getting, one per day, right, completed, it's going to take 50 days to get through that stack of 50 engineering change orders. Now, what's particularly interesting in engineering change orders and in many, many service tasks that we do is not all pieces of work are created equal. Certainly in the engineering change order world, we have typically three different categories. We have engineering change orders that are related to safety issues that need to be done immediately. The second tier is engineering change orders that are related to fit or function. And then the third tier is just cosmetic changes. Now, if we've got an engineer that's piling their way through 50 different change orders, we've got a long lead time to get through those. Chances are supervisors are going to be asking how things are coming along, and so you end up with these engineers switching between different tasks. And so they do a little bit on this first one, then they switch to the next one and do a little bit on number 2, and then they switch to the next one and do a little on number 3. Then they have to switch back to number 1 to create a status update, and you end up switching around so much that you end up losing a lot of time that could have been productive time simply because you're switching between tasks all the time. So with a work control system, we can put a WIP cap over the process here. And a WIP cap is simply that, a cap on the amount of WIP that's there. Con-WIP was the original term, constrained work in process. So we put some WIP. Those are the boundaries of our core process pull system here. And then everything else stays in queue out here. So we might have a whole pile of engineering change orders in queue, and we can prioritize that queue and put the safety-related ECOs to the top, and then the form, fit, and functions in the middle, and the cosmetic items can be at the bottom. If we then limit our engineers to, say, 2 engineering change orders that are on their desk, then our lead time to get those through, instead of 50 days, becomes 2 days. And so 2 days to get through the process, one exiting every day. So every day we can take a look at that prioritized queue and say, is there a new high priority item that needs to be worked on? If so, introduce it to the process. And we're getting entrance into the process every day, knowing that they'll be done in 2 days. And so what that eliminates is needing to go in here, over-manage these engineers, and tell them, oh, this one's really, really hot, we need to work on it right away, and have them break the setup of whatever they're working on now in order to get to that hot item. Instead, we simply manage everything in the process, just operates as normal, and the next highest priority work goes into it from this prioritized queue. And so that's a very common implementation, and the mirrors of this that we see outside of an engineering department, we might see this, well, this is exactly how an emergency room works, right? We have some number of doctors or some number of beds in an emergency room, and we have a prioritized queue in the waiting room. And we limit the amount of work that goes into these beds, either physically because we only have a few number of beds in the emergency room, or we limit based on the number of doctors and nurses that are available, and the rest of the folks sit out in the waiting room and are queued on the priority of their needs. Now, the downside of this is that somebody that comes in with a relatively minor injury might spend a fair bit of time down at the bottom of this queue. And no doubt about that, that would be a dissatisfying result. And so we might need to consider having different channels that we run things through as well, where we can, again, put our core process pull systems in place, but also segment our work so that we can move different types of work through different channels, ensuring that we don't have somebody that sits basically forever down at the bottom of this queue because their need is relatively little compared to the traumas and the broken legs and whatnot that get prioritized to the top of the queue. So the emergency room operates like this already, and then certainly in when you call in many call centers and things like that, the nature of the call that you have coming might bump it into a different place on the queue based on whether you're trying to get technical support or trying to give them money, and they'll bump you to a different level in the queue. Certainly with the airlines, if you're a frequent flyer, you will be bumped to a different level in the queue based on your frequent flyer status and whatnot. So we see prioritized queues used with core process pull containment systems in many, many different organizations. And really there's no place that I can think of that wouldn't benefit from looking at the process from this point of view.
Lars, from what you've just been talking about, what about how would you account for a shared resource in the calculations? That, like, for example, where you have two product families that use one shared resource rather than breaking it out.
Right, okay. Yep. So a scenario like this where perhaps we have some steps in a process like this, shared resource, and another process down here, and then they all come together and are sharing that one common resource and then come out here again. And perhaps they break out and have additional steps like that. So in this type of a scenario, we really need to start now thinking about the amount of WIP and the core process pull sizing. Two different ways we can approach this. One is we put a system that bounds this entire process. And so we go from beginning to end, right? And our core process pull system and our cap on the amount of work in process allowed in that system is going to span the entire process. And our queue for what we get to start next year will be a prioritized queue that will feed either to that process or this process only when we have an exit either here or here. And we have a completion, and that completion authorizes a start. So that's one scenario where we actually put a work control system over the entire process, and that's a pretty common implementation like this. I've done this type of implementation in heavy manufacturing where we have lots of welding going on multiple different lines, but then we come to a common machining center, and that common machining center is the bottleneck. And so we cap the entire building and just then manage this prioritized queue based on due date. And if we have identical due dates, then we start looking at nuances of customer and perhaps profitability and things like that. So that's one option. Another option is that we can simply put the work control right here and put our core process pull system just over that system there, so that we are really gating that process and we have our prioritized buffers here, and then we put a second work system, a core process pull over each of these sections here, so that we limit the amount of WIP that can build here, we limit the amount of WIP that can build here, and then we limit the amount of WIP that can be in queue and going into this bottleneck process here. Allows these two processes to operate a little bit more independently, but still, when this queue gets backed up enough so that we've reached our maximum WIP in this center bottleneck area, then that will stop all of these processes up here, because nothing will be able to leave and go down into these into the center bottleneck process. So that's another way that I've seen it implemented. But the third way that I've seen this type of an implementation, and I've not done one of these myself, but this was actually where we take of our shared resource, we actually allocate a certain amount of capacity in the form of physical cards. And so this process might get say 4 Kanban cards, and this process might get 3 Kanban cards. And so if they send a piece of work in with a Kanban card attached to it, until it leaves here and that Kanban card returns back, they don't get to start another piece of work. And so we can actually split the proportion of capacity in that shared resource, specifically based on some ratio determined by the number of cards or whatever other mechanism we use to split that capacity.
All right, couple more questions. One that goes back to what you were talking about in terms of computing the optimal WIP. Is there a way to do it mathematically? You talked about error. I think there's a question to, can you specify a little more on that?
Yeah. So this is a question of, we can mathematically calculate that starvation boundary, right? And then we have this area of the curve here up to this excess boundary, and we don't have a way to mathematically calculate that excess boundary. That is something that we can only observe, and that can be very dynamic. It can move over time, and it can be very operator dependent as well. So how to figure out where to be in this range, that is something that is difficult in some cases and impossible in most to specifically mathematically calculate. The reason being is we in almost every process we do have variation. So we can, for some degrees of variations, so processes where we have relatively well-behaved demand variation, and so by well-behaved, I'm not talking about normal, I'm talking about demand variation that is perhaps Poisson, and 2 S's in there, and then service variation, so the time it takes us to do our service, if we use an exponential distribution for that. When we have very well-behaved mathematical distributions and our reality actually matches those distributions well, then the math is tractable enough that we can do the math and calculate the queuing effects. And when we calculate those queuing effects, then we could get ourselves into a pretty close answer mathematically of how much WIP we think we need to have in the process based on the queues that we expect to build, based on well-behaved demand and service. Unfortunately, now that queuing theory works well for relatively straightforward systems with well-behaved distributions. It starts to fall apart when we start having systems like such, where we have multiple streams coming together, and perhaps where we have not well-behaved processes. So perhaps we have a service process that we modeled as, say, a log normal, But in fact, no distribution, no process is going to operate as a log normal because we have some minimum here, value-added time, that will never take below value-added time for our service, right? So it's already truncated on the left side, and chances are it's truncated on the right side also because if something starts to take too long, management is going to intervene and we're going to change the process. The rules are going to change. Or we almost always end up with some sort of modified distributions, really, representing both our demand and our service. That's, the places where we see mathematical distributions really operating true to themselves and our process operating very well that way are very, very, very high count transaction environments. So stock market trading and things like that, where we're talking about millions of events happening per minute or per second, then things start to look like real mathematical distributions. But in most of our human world, things aren't moving that quickly, and we're going to end up with distributions that aren't so well behaved. We're going to end up with discontinuities where we get to a particular point, and then we move to a different point, and then we move to a different point. And so these discontinuities will just throw the system, the mathematical calculations, into a tizzy, and it makes it very difficult to actually come up with accurate numbers there. There are some informations out there that can help us out, and there's a fairly large body of mathematical work on queuing theory that can come in handy. However, really, in most cases, because our processes are going to be muddled up with a number of different entrants and different flows and different rules and different possible decisions and changes and whatnot, what I've really found over the years is that being able to relatively quickly build that process in a simulation engine and then perform what-if scenarios on that simulation engine of that process, that's a good technique for getting an understanding of about where that work in process is going to fall, and then advocate always starting at the high end of a process estimate and then slowly, incrementally working our way down, letting the process stabilize at each of these new points so that we can really make sure that our model is accurate enough and we truly understood the process. All models are wrong. Some of them are useful. We live in a world that looks something like that, and we build models that look something like this, right? And so our models can never be a full representation of reality. They can only be a reasonably good or reasonably close representation of reality. We make some informed decisions from those models, and then we conservatively test the results of that in real life and work our way down.